Okay, are you ready, Fredi?
Yes, I'm ready. Thank you. Yeah.
Okay, perfect. So let's start. And okay, so I will introduce. Is that okay? Okay.
Yes, please.
For being here.
Yeah. So today we have the pleasure to welcome in this Zoom conference Fredi Tröltzsch from the Technische Universität Berlin. We will speak about optimal control problems with controls appearing nonlinearly in an elliptic state equation. So thank you, Fredi. And before we start, I would just ask everyone to close your microphone if it is not done, so that we will not have any problem during the talk. Well, so thank you very much, and please, Fredi.
Okay, thank you, Sylvain, for the introduction. And it's my pleasure to give a talk in this webinar. And it is joint work with Eduardo Casas from Spain. And I should extend the title of the talk a little bit. Yes, controls appearing nonlinear in the state equation and not in the objective functional. And this combination gives quite an interesting number of questions. So let me start first with a little, oh, what's now? This does not work. Why doesn't my...
Can you put your mouse on the thing?
Oh, just a moment. Yes, okay, thank you. Yeah, thank you. Well, the outline of my talk is as follows. First, we introduce the optimal control problem. Then there is something to say about the state equation. The first main point is on the existence of optimal controls. That is here a little bit more different from other problems. Next, a short sketch of necessary optimality conditions. And then comes the next main point, namely sufficient optimality conditions for different situations. And finally, an application to the convergence of numerical approximations of the problem. So let me first start with the optimal control problem. We want to minimize a objective functional, j of u, that is the integral over this L function that depends on the state associated with the control u. So y sub u always denotes the state associated with u. And the state equation is an elliptic one, and semilinear elliptic one. Here you have an elliptic operator. It is defined here, standard elliptic operator with uniformly elliptic, uniform ellipticity and bounded coefficients. And on the right-hand side, we have a nonlinearity where control in particular is appearing, and of course the state. I will speak about the assumptions later. This is the Neumann type boundary condition with a co-normal derivative dNA. And the control is in L infinity of the space-time cylinder, and it is bounded from below by a constant alpha and by another constant beta from above. Omega is a bounded set of Rn with a boundary, 2- or 3-dimensional, and while alpha and beta are real numbers. Okay, this is the main points we have here. And once again, the same problem. Yeah. The state is considered in H1 of omega, intersected with L infinity. L infinity is needed to make the nonlinearity is well defined, and the control, as I said, is bounded. Well, what is the main difficulties? The first main difficulty is how to show the existence of an optimal control. Because the standard proof that is done in the majority of papers on optimal control does not work here. The reason is, if UK is a minimizing sequence that is converging weakly to some control U, then you cannot expect that the nonlinearity is also converging weakly to the same function f of u. This is just the lack of weak continuity of nonlinearities. So this method of proof would fail. Then the next is can we expect that a stationary control, that means a control that fulfills the first order necessary conditions, obeys the coercivity of the second order derivative that is needed for second order sufficiency? We will show, yes, we can expect it, but it is interesting. If f is linear with respect to u, then this is known to be impossible. So here, the nonlinearity, the nonlinear appearance of a control in the state equation helps. We'll see it by examples. And another question is, what about convergence of numerical approximations? So our main results here are the following. We prove the existence via the Filipov selection theorem. Then we confirm by associated analytical examples that really second order sufficiency can be induced by the nonlinearity f in the equation of the right-hand side. We will see some sufficient optimality conditions for bang-bang controls, new versions of second order sufficient conditions, and a convergence result for numerical approximations where we also use the Filipov theorem, and this is also new. First, a few words on the assumptions on f and L, on the nonlinearities. Well, f is a Kara-Theodori function that is of class C2 with respect to the state and the control, and of course, measurable with respect to x. The derivative of f with respect to the state is supposed to be non-positive. This is just monotonicity that we need for the existence and uniqueness of the equation. And if we insert the 0 for state and control, then this function should be in LP bar of omega, where P bar is greater than n by 2. This is just needed to get, in particular, L infinity results for the state. And the integrand in the objective functional is also supposed to be Kara-Theodori of class C2. And here, inserting the 0 state, it should be in L1 of omega. And moreover, we need certain Lipschitz properties of the derivatives and also some integrability. It would take too much time to present all these things. We just assume associated natural assumptions, so that in particular the control to state mapping is C2. And under these assumptions, we obtain the following theorem. Namely, for every u that is bounded, the state equation has a unique solution, which is in H1 intersected with this Hölder space, where the Hölder constant is between 0 and 1. And it is, which is important, independent of a control u. Moreover, we have a boundedness. So all states are bounded in H1 and in this Hölder space by this right-hand side, independently on the control. So this is helpful for certain convergence. And if we have a bounded sequence in L infinity, bounded sequence of controls that converges to some u in L1, then we have still convergence of the states in H1 and in the Hölder space. In principle, this is not that surprising, because if the controls are uniformly bounded, then the control in L1, convergence in L1 implies convergence in LP for all p less than infinity, and so we are in the range that we can expect such results. Let us define the control to state mapping by G. It associates the state y sub u to the control, and it's considered from L infinity to this space. And one can prove that the mapping G is of class C2. So we have second order differentiability that we need for second order sufficient conditions. And the derivatives, this is not surprising. This is not new, this result, in some sense. Under our assumptions, our objective functional, the reduced functional, depending only on the control, is of class C2. And the first derivative looks like that. I think this is well known. We have an integral over the adjoint state. I will show the adjoint equation in a minute, multiplied with the derivative of a nonlinearity with respect to u, taken at y sub u and u. This is the direction. Please notice this is only in L infinity. So the differentiability is only in L infinity, at least in general. And the second order derivative looks a little bit more complicated. I think it's not necessary to understand now all the terms. What do we see here? We see, of course, second order derivatives of L and F. We have once again the adjoint state. And ZV1, ZV2 are the linear solutions of the linearized equations with respect to the directions V1 and V2. That means these are the derivatives of a control to state operator taken at U. And phi sub u, as I said, is the adjoint state, and it satisfies this equation where on the right-hand side, the derivatives with respect to the state of F and L appear. So adjoint differential operator, adjoint conormal derivative. So this is that result on the differentiability. Now, existence of optimal controls. Let me start with a very simple counterexample that shows that the nonlinear appearance of a control is a little bit delicate. We consider this linear equation for the state, but the control is appearing on the right-hand side in a quadratic way. And now we select a sequence of bang-bang control functions, bounded, of course, that only take the values -1 and 1 and converge weakly to 0 in L2 of omega. Okay, this is not difficult to find such a sequence. And what happens? Well, no matter if -1 or 1, the right-hand side is always 1. And so the solution of the state equation is, of course, yk equal to 1 for all controls, because this is 0, this is 1, it fits, and the normal derivative is also 1. So we have a stationary sequence. It is already arrived at the limit, 1, but this state is not the state associated with a weak limit control u tilde equal to 0, because if we insert here 0, then the state is 0. So this is the main problem in a nutshell. But maybe you would say, well, this is a linear equation, it's a little bit too simple. So let's consider a little bit less naive example. And it is of a type that we will see later on also for nonlinear examples. Here in this equation, where the state now appears under in the form e to the minus y, here we insert the same sequence that we had in the last example. And once again, this problem, the states yk solve this equation because u squared, once again, is always 1, so you do not see it here, plus the uk here on the right-hand side. And this converges, uk converges to 0 weakly. This converges to the solution of this equation. And the solution of this equation is not 0, because for 0, we would have a 1 on the right-hand side and a 0 on the left-hand side. This does not fit. But the convergence of yk is not 0, so it does not converge to the state 0 that is associated with a weak limit control u tilde equal to 0. Because if you insert here the limit control, this is a 0, this is a 0, the state would be 0. So once again, we have the same effect that we don't have weak convergence in the right way. So it's clear from these examples, the standard way of proving existence of an optimal control with weak convergence does not work. And the key for solving that is a very famous lemma by Filipov, published in 1959. It is the following. We take a set measurable subset of Rn, for instance, like our omega, a compact set of Rm, and the Caradeo-Dore function f, so it's measurable with respect to x, continuous with respect to u, that maps into RL. And we assume that we have a function j, omega to RL, such that j of x is an element of this set-valued mapping, this set for almost all x, so f of x and k compact set. And the result is that we have a measurable function u from omega to k, such that we have this representation, so that j of x is f of x and u of x. It is clear that we have such a function u of x because for all x, there must be a number u such that j of x is f of x and u. But the mapping from x to u must be measurable, and this is the main point of this theorem. And it's called, this u is called measurable selection. I think that many of you will know that theorem. And the application of Filippov's lemma in optimal control is not new. When I wrote my first lecture on optimal control of ordinary differential equations, I used this nice book by Mackey and Strauss on optimal control, and I learned about that lemma, and I presented it also in the lecture. It is also this method is also to be found in the book by Cesari, and about 10 years later, we found the same thing in the control of PDEs, for instance, in a paper by Papageorgiou on the control of nonlinear elliptic equations, by Epler for parabolic, and Epler and Unger once again for semilinear elliptic equations. And I should also mention some recent trends in this set-valued analysis, for instance, by Frankowska, Rampazzo, and others, where such methods are used. I think that this is a little bit ignored in the control community of PDEs, and therefore I think it's nice to present this application here. The theorem is the optimal control problem has at least one solution. And let me sketch the proof. Like in the calculus of in the direct method of calculus of variations, we first select a minimizing sequence. That means a sequence of controls, admissible controls, such that the objective value tends to the infimum of the problem P, of our control problem. Because of boundedness, it's clear that a subsequence of states converges weakly in H1 of omega. Say this is the state sequence itself. And it converges also strongly in C of omega bar because we have this compact embedding from the Hölder space. Okay. And what is also not difficult, the objective values to UK, we know they converge to the infimum of P. We are equal to this. The controls do not appear in the objective functional. And because of convergence in this space, we obtain that this tends to the infimum. Okay, so in principle, we could stop and say y bar of x is the optimal state. But the main problem is we do not know that this is a state. We have to find a control such that this state is associated to that control. It remains to show that we find an associated control, and then it's clear then u bar would be optimal. And for that, we use Filippov's lemma. We consider this set-valued mapping, the multifunction capital F, where we take the limit for the state. And this is the set alpha beta, the set of all possible control values. It's, of course, compact. And by the continuity with respect to this variable, also f of x is a compact interval. And this is just that we are in the situation of a Filippov lemma. We define a sequence of functions gk that is obtained by inserting the minimizing sequence of the controls in the right-hand side. And then it's not difficult to show by boundedness that we have that a subsequence, once again, let us assume this sequence itself, converges to g bar, to some function g bar in some space LP of omega, and by convexity, that this function belongs to this set for almost all x. Okay, now we are in the situation of a Filipov lemma. We find a measurable u bar that maps also into this set, so it's automatically admissible, such that we have g bar of x is equal to this term. So in principle, the proof is then almost finished. We finally have only to show that y bar is associated to this u bar. This is the main idea of the proof, and this gives existence. Next step is a little bit on necessary optimality conditions. This is more or less standard. So first we introduce the Hamiltonian function on omega times R3 into R. It depends on 4 variables: space variable x, number y, number phi, and number u. Is obtained by adding the integrand of the objective and plus phi multiplied with f of x and u. And y and phi and u are just the placeholders for the associated functions. And the theorem is, first part of the theorem, if u bar is a local minimum of our problem in the LP sense, and p can be between 1 or infinity, all values, then we obtain this standard variational inequality, namely that this product between the first derivative of h with respect to u and all possible differences of admissible controls this integral is non-negative. If you would consider the pointwise version without that integral, this is sometimes called a weak minimum principle, weak because the derivative of h with respect to u appears. There is also a strong form. If p is less than infinity, then we obtain the Pontryagin principle that says that the minimum of a Hamiltonian function where y bar and phi bar are inserted, minimum with respect to s, this is a control variable, is attained for almost all x in omega by u bar of x, at least by this control. Now, this is proved via diffuse perturbations. And second order necessary condition is obtained as follows. We have to introduce a critical cone, namely all directions v in L2 of omega that are orthogonal to the reduced gradient and satisfy the following sign conditions, namely the direction must be non-negative if u bar is at the lower bound, and it's non-positive if u bar is at the upper bound. This is quite natural because u minus u bar has these properties. And this is a theorem from a paper of Eduardo and myself from 2012. If u bar is a local solution of p in the LP sense, once again, p some value between 1 or infinity, then the second derivative of u bar in the direction v squared is non-negative for all v from the critical cone. These are the necessary conditions, and they should be quite close to the sufficient conditions. This is why it's interesting also to have these conditions. Let me now come to the sufficient optimality conditions, which is one of the main parts of this talk. But let me start with a few words on the role of second order conditions, because Eduardo and I were often asked why they are needed. Is this really useful? And I would say that they are in their behavior a little bit similar to constraint qualifications in constraint optimization. Constraint qualifications are needed for the analysis, for instance, to prove the existence of Lagrange multipliers. But for nonlinear problems, in general, they depend on the unknown solution. And so they are difficult to confirm, at least not a priori. And this is similar for second order conditions. And second order sufficient conditions are just an analysis tool. And for instance, you can use it for the following questions. First, if you have a stationary point, so a triple that satisfies the optimality system, then you can verify by second order sufficient conditions that this point is a local minimizer. Well, this is, for instance, in exercises, if you construct examples for with analytically known solution. The next thing is, if you have discretizations of your optimal control problem, and you want to show the convergence of optimal solutions if the associated mesh size of a triangulation is tending to 0. You cannot expect to have such behavior, at least for non-convex nonlinear problems, if you don't have a second order sufficient optimality condition at the unknown solution. And another property is that second order sufficient optimality conditions ensure local uniqueness of minimizers. It would be very difficult if you have the situation that the minimizer is the accumulation point of infinitely many other strict local minimizers. For instance, numerically, this would be a nightmare. And you will also need second order conditions if you want to prove numerical algorithms, such as the convergence of semi-smooth Newton or methods or SQP methods. And then the question arises, can we confirm them numerically? And I would say in principle not, because it's impossible to deduce the second order coercivity of a second order derivative from finite dimensional computations, and you have to compute in finite dimensions. Therefore, it is hardly possible to confirm second order conditions numerically, unless you know it by analysis. Okay, so this is a little bit on the meaning of sufficient conditions. Let me now start with a first type of sufficient conditions, not necessarily second order conditions, tailor-made for bang-bang solutions and L-infinity local solutions. And we need here a structural assumption. Just consider this term. This term is appearing in the variational inequality. We know if this is positive, then the control is at the upper bound. If it's negative, if it's positive, it's at the lower bound. If it's negative, it's at the upper bound. And if it's 0, well, we don't have we cannot see what the control is. So the zeros are a little bit the troublemakers of the optimality conditions. And we assume that the measure of the points such that the absolute value of this term is less than epsilon can be estimated from above by a constant k and epsilon to the power gamma. The gamma is something positive that can be infinite, and this should hold for all epsilon that are sufficiently small. This structural assumption is needed in the sequel for proving sufficient optimality conditions. We can take gamma to infinity if the measure is 0 for some epsilon greater than 0. Well, it's clear if we have here infinity, this term is 0, so we must have that this set is 0 for some positive epsilon. Moreover, if U bar satisfies this assumption, then the solution U bar must be necessarily bang-bang, because the set of zeros here has a measure 0. And we also can show, or it's easy to find, that we can use here gamma equal to infinity if we have a sigma such that the measure, a positive sigma, such that the measure of this set is 0. We will need that later. And the first theorem, it's more or less a lemma that we need later. If this structural assumption holds and an admissible control satisfies the first order necessary conditions, that means it satisfies the variational inequality, then we have that the directional derivative can be estimated from below by the L1 norm of a difference to the power 1 plus 1 by gamma. And this for all admissible all admissible controls. And the constant kappa here can be explicitly given. Well, we have here a growth rate. We know from the first order necessary condition that this term is non-negative. It must be non-negative, but here we have a positivity and a certain growth rate. And let me show that. Let us define by omega epsilon as the set of all x such that this term here that is appearing under the variational inequality is greater or equal than epsilon. It's just the complement of our structural assumption. And then we have that omega minus omega epsilon has a measure that can be estimated against k to epsilon to the power gamma. And now we start with the term we want to estimate. This is, as we have learned, this term multiplied with the difference of u minus u bar. And we know already that this is non-negative in view of the first order necessary condition. When we shrink omega a little bit, we go to omega epsilon, so we reduce the integral. Moreover, we can, of course, because this is non-negative, we can take here the absolute values. And we know from our structural assumption, here we have it on omega epsilon, this is greater or equal than epsilon. So we can extract the epsilon and we end up with this inequality with this epsilon. And here, this is the integral over this absolute value. So this is L1 norm on omega epsilon. Now we want to go over to L1 norm of omega. So we borrow this and we have to subtract what we have borrowed, which is that term. And this stays. The maximal difference between u and u bar is beta minus alpha. That means that if this is alpha and this is beta, for instance. So we can extract that beta minus alpha from the L1 norm. And then there's an integral over L1, and this can be estimated by k epsilon to the gamma. Just look, here we have this assumption. Okay, so we finally have epsilon multiplied with L1 norm minus this term. Well, and now this is a little bit tricky. You can define epsilon by this value, and if you insert and compute a little bit, then you obtain just a statement of a theorem. And now we can use that to have a sufficient optimality conditions in principle for bang-bang controls. We assume that the structural assumption is defined, is satisfied for gamma equal to infinity. And if u bar and u satisfies the variational inequality, then we have a radius epsilon greater than 0, and the same kappa that we had in the last theorem, so that we have this estimate, namely for all u that are admissible and are in an L-infinity neighborhood of radius epsilon around u bar. And this is clear. This is always positive if u is not equal to u bar. So u bar is a strict local optimum, and because of this neighborhood, in the sense of L-infinity of omega. So this is a sufficient optimality conditions for U bar. That of course has to satisfy the variational inequality. And once again, let me show you the main part of the proof. We take such an U in a neighborhood of U bar, and admissible, of course, and the epsilon will be fixed later. Then we perform a Taylor expansion at the point U bar. So this is a fixed term, this is the first order term, and this is the second order term with some intermediate point. This means with some theta between 0 and 1. This can be estimated thanks to the last theorem in this way: 1 plus 0, because 1 by gamma is 0 because we have assumed that gamma is infinity. And this can be taken, can be estimated from below in this way. Okay. Then we do the following. Here we extract the L infinity norm, and there is then remaining the L1 part. So we extract the L1 norm from here and from here. And this L infinity norm can be estimated from above by epsilon, because this is a radius of the L infinity neighborhood around U bar. Okay. So we can estimate from below. In this way, we have J of U bar plus this number multiplied with the L1 norm of U minus U bar. And well, if we take epsilon sufficiently small, then this is positive and we obtain the result. An example for that. We want to construct an example with the local solution in the sense of L infinity of omega. And more or less, the way how to construct such examples is well known. We want to minimize here a quadratic function with the given function yd that I will use later. And we take this state equation with some e omega that also will be fixed later. The control should be between -1 and 1. So alpha is minus 1, beta is plus 1, and omega is a square of length 2 pi. And now we say we want to have a certain triplet as a desired candidate for optimality. So this means a desired candidate that obeys the first order optimality system. So we select an arbitrary y bar in H2 of omega with Neumann's boundary condition 0, such that the C of omega bar norm is less than 3. Well, you will see later why we do that. For instance, y bar identically equal 1, or this product of cosine functions would do the job. We say we want to have this adjoint state, namely -1, and the control should be a bang-bang control, which is +1 in the lower left sub-square and the upper right sub-square, and it's just -1 in the complement. These are the functions we want to have as optimal candidates. And we construct the problem around this triplet. That means next we fix yd and e omega such that this triplet that we have fixed here really obeys the first order necessary conditions. Okay, this is quite easy. If we insert y bar, what we have taken in the state equation, and the u bar also, then we obtain this function. I don't have to compute it. It depends on which y bar we insert. The same thing is with the adjoint equation. We insert y bar in the adjoint equation and also phi bar and obtain this yd. It's also well defined. And now we set sigma as this term. Here you have the difference of e to the power minus y bar, c of omega, this norm, minus e to the power minus 3. And this is positive because we have assumed that this norm is less than 3. So this is larger than e to the minus 3. This is positive. And now comes quite a lot of computations. And we are able to find that the measure of this set, where this absolute value should be less than sigma, is 0. And so we can take gamma equal to infinity, because this is just sufficient for that. And then by the last theorem, we obtain that u bar is a strict local minimum of P in the L infinity sense. Please notice, L infinity sense means that all the neighbors in this neighborhood must have the same structure as u bar. That means the structure of the 4 subsquares must be conserved. Otherwise, they are not in an L infinity neighborhood. So this is a quite narrow neighborhood. Let's now go over to the L2 sufficiency. And here we will have finally an L2 neighborhood. And we assume that u bar in u hat once again satisfies the first order necessary conditions along with y bar and phi bar. And we assume a Legendre-Tröltzsch condition, namely the second derivative of a Hamiltonian taken at these points here should be greater or equal than nu, some positive nu, for all s that can vary between alpha and beta. This is a typical Legendre-Tröltzsch condition. The first part of the theorem says, if the structural assumption is fulfilled with some positive, some gamma that is greater than 1, then we have a positive epsilon, a radius again, for an L2 neighborhood around u bar, such we have this growth condition. J of u can be estimated from below by this sum of an L1 term to the power 1 plus 1 by gamma and an L2 term squared. Of course, once again, we have that u bar is a local minimum, either in this set space or in this space. And the second is a real pure second order condition, as we know it from literature. If we have this coercivity condition in some sense, the second derivative in all directions v is positive for all v in the critical cone that are not 0, when we find the radius epsilon for L2 neighborhood and the growth rate delta, such that we have this quadratic growth condition. And this means that u bar is a strict local minimizer, strict local solution in the L2 sense. I cannot give you a proof of this theorem. The proof is quite long. Instead, let us once again consider an example. And I said you at the beginning of my talk, there was a question, is it realistic to have second order conditions if the control does not appear here in the objective function? Or for instance, it does not appear as a quadratic Tikhonov term. And this example shows that this is possible indeed. Once again, we will fix yd and e omega in a way that a desired solution is the optimal. Well, in that case, the adjoint equation is given in this way. Once again, here on the right-hand side, we have the state, we have yd, we have phi. And we wish that this very simple triplet is a triple that obeys the optimality system. U bar should be -1. So the final optimal control should be U bar -1. The state is equal to 2, and the adjoint state is equal to 1. And now we construct once again yd and e omega in the way that this just works? Well, if you insert these numbers in the adjoint equation, well, phi is constant, so this is a 1, this is 0, this is minus e to the minus 2, this is 1, this is once again 1, and so on. And finally, if you do it, you get this value for yd. So yd is obtained by inserting the candidate into the adjoint equation. Now we consider the variational inequality. We have to know that u bar satisfies the variational inequality together with, along with y bar and phi bar. Well, here's very easy. The derivative of the Hamiltonian is obtained in this way. And if we insert here for y2, when we have e to the minus 2, and for u, it's e to the minus 2 again, and here's a minus sign, okay, it is 0. So the variational inequality is satisfied in a trivial way. And next, we insert y bar equal to 2 in the state equation, and then we find, just for completeness, this value for e omega. The main work, really hard work, is to evaluate the second order derivative. I have shown you the form of the second order derivative at the beginning of my talk. If we do that, we obtain this quite complicated behavior, a complicated form, where ZV is once again the derivative of the control to state operator with respect to V. And here you see the other terms. We insert the concrete values for phi bar and for u bar and for y bar in this term, and obtain finally this form, where you only see the direction V and the linearized solution ZV. And now it's not difficult to estimate this from below. We get this estimate. And this is the desired coercivity that we want to have for the second order derivative of our objective function. This looks good. And moreover, if we evaluate the second order derivative of a Hamiltonian with respect to the control, then we obtain, by inserting the concrete values, this value. So the Legendre-Tröltzsch condition is satisfied as well. And this means the control u bar is not only stationary, it is locally optimal in the L2 sense, because it satisfies a second order sufficient optimality condition. So this example shows that we do not have a theory that is empty. Finally, let me say a few words on the conversions of numerical approximations. We have to assume a little bit more. We assume that omega is convex in Rn, once again, n of dimension 2 or 3. We assume that it is polygonal if n is 2, or polyhedral if n is equal to 3. And we need also a little bit more smoothness of the coefficients of the differential operator, namely they should be Lipschitz. And we assume also that this is in L2. Then it's known that the state belongs to H2 of omega. And we have also boundedness in H2 for all possible state functions that can be associated to an admissible control U. Now the set omega with spatial domain is triangularized. We define a family, a quasi-uniform family of triangulations, tau H, where H is the mesh size. This is defined according to the book by Brenner and Scott. And we have finite dimensional ansatz spaces for the states. As usual, in finite element methods, we take the functions that are continuous on omega bar and are linear in each triangle of the triangulations. And for the control, we do not use this. We use piecewise constant controls. This means all the functions in L infinity that attain a constant value on each single triangle of a triangulation. We discretize the discrete admissible set for the controls is given in this way. We take all the functions which are piecewise constant and are between the values alpha and beta. Okay, then just for defining the discretized problem, we take this bilinear form that is associated with an elliptic differential operator to have a weak formulation. And then the discretized state equation is given any u in L infinity, it need not be discretized. We define by yh of u the solution of this finite element problem, where you have here the discretization of a differential operator, and here you have a nonlinearity. This is a variational equation for all zh in yh. The discrete problem comes later. The existence and uniqueness of a solution of this discrete equation can be first proved existence by the Browder's fixed point theorem. And the uniqueness follows from the monotonicity of F and the coercivity of A in a standard way. So also for the discretized state equation, we have existence and uniqueness. And the discretization of the optimal control problem, pH, we want to minimize this integral where the discrete state is obtained here and the minimum is taken over all piecewise constant controls that belong to this set between alpha and beta. Okay, and this is the theorem on the behavior of this problem. First of all, for any mesh size, this discrete control problem has at least one solution, UH bar. Well, this is easy because the admissible set is compact in Rn, NH, where NH is a number of triangles, and the control to state mapping is continuous. So we obtain this as a conclusion of a standard Weierstrass theorem. Moreover, if we have a sequence of states with controls associated with the controls, then this sequence is bounded in H1 intersected with continuous functions on omega bar. And the main point is that if HK is a sequence of mesh sizes tending to 0, and Y bar of HK is a sequence of associated optimal states, we can, of course, extract a weakly converging subsequence by boundedness in H1 of omega. If we have such a convergent subsequence converging to Y bar, then there is an optimal control U bar of P such that Y bar is the associated state. And once again, this cannot be proved by weak convergence of the controls. So we do not claim that the controls associated to these functions converge weakly to U bar. Well, this will be once again an application of the Philippov theorem. And moreover, we can finally say that the states converge even strongly in H1 of omega to Y bar, because it's known weak convergence is not very useful in numerical analysis. Very briefly, let me sketch the proof. Of course, by that part, what we want to show, we apply Philippov's theorem, as I said. We consider again this multifunction that we had at the beginning. And we also consider this a set S. It's a set of all G in L2, such that G of X belongs to this set-valued mapping to the set for almost all X in omega. And this is convex because of the interval structure enclosed in L2 of omega. We consider this sequence where UH bar are the associated optimal controls of a discrete problem. And here we take a limit for Y bar. Then all these elements belong to the set S. They are bounded. We have weak convergence, weak closeness, and so we can assume that the GK converge weakly to some G bar which belongs to S. And now, once again, same thing as before. By the Filipov theorem, we can prove that this G bar belongs to an admissible control, measurable control, U bar of X. And then the proof is completed by showing that Y bar is indeed the state associated with U bar, and also that it attains the minimum. And this shows that U bar is an optimal control. I think this trick to apply the Filipov theorem for the convergence analysis is also a novelty of our paper. And this is the end of my talk. I would like to mention a few references. First, the paper I reported about with Eduardo Casas is appeared in SciCon, and two papers of Eduardo Casas, Daniel Wachsmuth, and Gerd Wachsmuth that paved the way for the sufficient conditions for L-infinity controls, for bang-bang controls, that are published in 2017 and 2018. And now I arrived at the end of my talk, and I thank you for your audience. Thank you.
Well, okay. Sorry. I will put my camera on. So, yeah. As usual, I'm the only one who can who upload, but I'm sure that everyone will like to upload too. Okay, so if there is any question, please raise your hand if you know how to do it, or open your microphone and tell me if you want to ask one question. Okay, so let's wait a little bit more about the questions, but I will ask one maybe. In your at the beginning, you were mentioning some kind of counterexample to convergence.
Yeah.
On an elliptic equation in which you had a source term like exponential y times u squared, or something like that.
E to the minus y u squared, yeah.
Yes. And so if I understand correctly what you said, so you have the convergence of the control to 0, the weak convergence to 0, right? But the corresponding states do not converge, right?
They converge. They converge in H1, for instance, but they do not converge to the limit state that is associated to the weak limit of the control. This is the interesting thing.
Can you go back, please, to that
Oh,
example?
yeah, I try. Let me do. How to do? Yeah, I do this, and then I have to go back. Here's the beginning. I was too fast.
It's close to here, right?
Yeah, our main result is still blah, blah, blah at the beginning. And assumptions. Now comes state equation. It's still not that. And now should soon come existence of optimal control. And this is what you are looking for, right?
Yeah,
no, not that. The more less naive example. Okay.
Yeah, so on this one, you are saying that, okay, so you take u as a 1 and minus 1, it will converge, right?
Yeah, so you have this equation.
And so if I understood correctly, the solution of minus Laplacian y plus y equal to exponential minus y in omega should be something that can be achieved with some u, right?
This is a question, finally. Well, I do not know if so easily.
But isn't it the content of Filipov's theorem?
Well, if you take here the control, it's not the control 0, but it's not that easy. This is not the contents of the Filipov theorem. The Filipov theorem said we find a certain control for this function. Now let me see, how can we obtain this here? Here, this varies through alpha beta. In the moment, I'm not able to answer. What is that here? This is not the real case of a Philip of Lemma, I think. So I'm a little bit unconscious. We should have that this term, or this term here, is all the time element of the nonlinearity with u taken in alpha beta. And here we don't have alpha beta in the moment, by the way. Huh?
No, but I thought that
we mean we have bang-bang controls.
1, right?
Yeah, we have the bang-bang controls. It's between -1 and 1. Yes. And we have to check now this term where u varies between alpha -1 and 1. So all and also here. We would have to evaluate that. So u squared plus u. Yeah, we have to evaluate that, and then we should find that. But in the moment, so sitting in front of my screen, I cannot easily find.
May I say something?
Oh, Eduardo, nice. Yeah, please help me.
Yeah, you have to select u such that exponential of -y times u squared plus u is equal to exponential of -y. Okay?
Okay.
Yeah.
Then you multiply this identity by exponential of -y and pass everything to the left, and you write the equation u squared plus u exponential of y -1 is equal to 0. This is a second degree equation in u that you can solve, and you get the unit.
Yeah.
You understand?
So it corresponds at the end to some u bar, say, which is related to y, right?
Exactly.
And which is not 0. Okay.
Exactly.
Yeah, but it's
okay.
So it's not that easy to find. Thank you, Eduardo. Yeah.
Okay. Yeah, thank you. Okay. Are there any other questions? Well, if not, let's thank the speaker again.
Please.
Yes.
One thing.
Yes.
The example you found at the end, where you have that the second derivative of u bar times v squared is greater or equal than some norm of some constant times the norm of v squared.
Yeah.
You are able to do that because you have these cross derivatives. Is it? That's the difference. I don't know if I have explained myself properly. In the end, you have this example where you see that okay, the second order conditions you have are not empty.
Yeah.
And in the example, not the theorem, in the example that you showed, no, in the end.
Yeah.
Here, at the end of this example,
Yeah.
Go on.
Yeah, we have this.
Okay, here it is because okay, I see between the brackets, the square brackets, you have all these cross terms. So finally you can find this. So I see.
Yeah, we can estimate it. It has some relation to a complete square and something else, and then you can do that.
Yes, but I was wondering. Okay, wait, how can we get this when u is comes non-linearly, and we cannot have this when u comes linearly?
Well, but there is a known theorem that if u is only linear in the equation,
yes,
and it does not appear as an Tikhonov term in the objective function, then there is a known theorem that this coercivity cannot happen. You can
yes, that's what was so surprising to find it there.
Yeah, but this is.
So I see why now. I am seeing why. Yes.
Yeah. because the control is appearing nonlinearly. This helps. Otherwise, it's impossible.
Yes, I see. Okay. Thank you. Very nice talk.
Thank you, Marianne.
Thank you. Are there any other questions? Well, okay. So if not, yeah. So thank you again for your very nice talk.
Thank you all for coming, and have a nice evening.
Yeah, you too. Thank you. And so thank you all for participating.